I don't know what happened to our second video, so I'm re-recording this. For the second half, we're going to cover the remaining examples. We covered 1 through 4 in the first video, so this second video we're picking up right here after example 4, and we are talking about just the different ways to denote a function, the notations that are used. You can see some of the common examples here. We have f of x, again f of x. We can use capital letters, we can use lowercase letters. There's no real limit to what you can do as far as how to define a function. For example, this one right down here, we have f of t equals t cubed. That could be a function of time. I don't know. You know, sometimes you want to use a variable that makes sense in the context of the problem that you're dealing with. But that notation makes it easy to evaluate functions as well. So what we're going to do in example 5 is evaluate this one function, f of x equals 2x squared minus 3x, at 4 different values. So for part A, we're evaluating this function at f of 3. So that's just in when x is equal to 3. So we take our original function and we replace x with 3 in every case. And then we just evaluate it and simplify. 3 squared is 9, 2 times 9 is 18, 3 times 3 is 9, so we end up with 18 minus 9. And when we evaluate f of 3, we get that it is equal to 9. For part B, we're evaluating it at 3x. So we take every instance of x in our original function and we replace it with 3x. And when we simplify, 3x quantity squared is going to be 9x squared times 2 is 18x squared. 3 times 3x is 9x. And that's actually it. That doesn't simplify any further. We could factor it. We could factor a 9x out, and we would have 2x minus 1. Either answer, since it wasn't specified to simplify or reduce or factor or anything like that, either one of those answers will be acceptable. Both factors or both terms share a 9x in common. The example, or for part C, is we're going to evaluate it at x plus 3. So we take our function and we replace every case of x with x plus 3. And then we start to simplify. Now the x plus 3 quantity squared, we've talked about this before. Remember, that just means it's x plus 3 times x plus 3. When we do that multiplication, we get x squared plus 6x plus 9. Distribute the negative 3, so minus 3x minus 9. We'll distribute the 2. And we get 2x squared, combine like terms, so 12x minus 3x, 9x, 18 minus 9 is 9. And that is the answer for part C. Part D is a special property or a special equation. It's called the difference quotient, and that will appear a lot when you start a calculus course. So when you take calculus 1, which I expect all of you to do, you will see the difference quotient a lot, and it really throws a lot of people off. And it's not because it's something complicated to deal with. The algebra is sometimes where the mistakes are made. So you just have to be really careful with how you simplify this. So I'm going to do this in 2 colors to kind of help break this apart. So we have this f of x plus h, and then we also have f of x, and then that's all over that denominator h. So let's do the f of x plus h. That tells us that we take our original function and we evaluate it at x plus h. So I'm just going to write this out here in red to match what we've done at the top. When I expand this, the x plus h quantity squared is going to be x squared plus 2hx plus h squared minus 3x minus 3h. Distribute the 2. And then I'm going to combine like terms. Let's see, it's plus 4hx. I don't have any like terms to combine, so sorry, I was distracted for a minute there. There's no like terms to combine on this one, so we will go on with the remainder of this problem. So in the numerator, we've already done this expansion and came up with this 2x squared plus 4xh or 4hx, whatever. And then in the purple is just our original function. It's just f of x. So there's nothing that we have to do to that. So we can rewrite all of this as 2x squared plus 4hx plus 2h squared minus 3x minus 3h. This is the step that normally when the mistakes are made, this is where it occurs. Because then we have minus, and it's our original function. So I always suggest that we put that original function in parentheses, because a lot of people will make the mistake of forgetting to distribute that negative through the parentheses there. All right. So now we will go ahead and distribute the negative. We get 2x squared plus 4hx. Now we can combine like terms. So our 2x squared and our negative 2x squared will cancel. Our negative 3x, positive 3x will cancel. And what we're left with is 4hx plus 2h squared minus 3h all over h. If you notice in the numerator, every term has an h, so we can simplify by reducing each term based off the h in our denominator, and what we end up with is 4x plus 2h minus 3. So that one does require a little bit more work and a little bit more careful thought and planning as you go through the steps, but it still just boils down to just basic algebra. So you just have to be careful with these functions when you're evaluating them, especially the difference quotient. Here we have a couple of different ways that a function can be represented. We have the implicit form and the explicit form. In the implicit form, we may have x and y on the same side of the equation. In the explicit form, we have y explicitly written as a function of x. And you can see that in this first example, we have y equals f of x, which is equal to negative 3x plus 5, whereas the exact same expression or exact same equation, it can be written as 3x plus y equals 5. That's the implicit form. The explicit form, we simply have it in terms of y in terms of x, or f of x in terms of x. When we're talking about the domain of a function, a lot of times that's another issue that arises that throws some people off. And the domain is the set of all possible x values that relate to that given function. For part A, it's really easy. Every single linear function, every quadratic, every cubic, every quartic, every quintic function, it doesn't matter what it is, when it's expressed in a manner like this, x squared plus 5x, we can choose any x in the world, and it's gonna work with that particular function. So the domain of any linear function, the domain of any quadratic function, is going to be all real numbers. So again, we can write this as x such that x is an element, that's that notation, of the reals. So that's all real numbers. Or you could write it as negative infinity to positive infinity. Either notation will be fine. For part B, we have a rational expression Rational expressions are also easy to work with. With a rational expression, you simply look at the denominator, provided that the numerator is a linear or a quadratic or anything like that. So with this one, the numerator is linear, so we just need to take the denominator, and we're going to set it not equal to 0, or you can set it equal to 0 and then just know which values to eliminate. X squared minus 4 is an example of the difference of two squares, and that factors really nicely into x plus 2, x minus 2, and then we can take each individual factor by the zero product property, set those equal to 0, and solve for x. And so what this tells us is that x cannot be negative 2 or positive 2. Any other value in the real number set is going to work. So as our solution, we can write x such that x does not equal negative 2 or 2. If you wanted to write it in interval notation, it's negative infinity to negative 2. Then from negative 2 to 2. And then from 2 to positive infinity. So again, either one of those notations will work. You can probably see why I like to set notation better, because when you get into the longer ones, it becomes a lot easier to write. For a radical expression, in this case, we're looking at a square root, and this applies to all even root functions. So if it's a square root, a fourth root, sixth root, you'll do the same process. You're going to take the denominator, or the radicand, what's underneath the radical, and you're just going to write it out as the radicand greater than or equal to 0. What's underneath that radical, since we're only dealing with the real number system right now, cannot be negative. So we want to make sure that it's either 0 or positive, and then we just solve this for our variable. In this case, it's t. So we'd subtract 4 from both sides. And then we're going to divide through by this negative 3. Anytime you divide an inequality by a negative, you flip the inequality. And what we end up with is t is less than or equal to 4/3. So in interval notation, it's going to be all t such that t is less than or equal to 4/3. In interval notation, it's going to be negative infinity to positive 4/3. And we put a bracket around the 4/3 because it does include 4/3. So again, either notation is acceptable. And then for our last one, we have, wow, I just zoomed in a whole lot. We have two different things going on here that we have to consider. One, we have to look at the denominator, and we have to look at the numerator. So first, let's look at the denominator. We have x minus 5, and like we said before on a radical expression, the denominator cannot be 0. So we know that x cannot be positive 5. But now we also have to take a look at the numerator, because this numerator, we can't have a negative value as the radicand. So we take the radicand and we set it greater than or equal to 0 and solve for x. So we subtract 12. And then we would divide by 3. And we get x is greater than or equal to negative 4. So we have to put these two pieces of information together. X has to be greater than or equal to negative 4, but it cannot be 5. So when we write out the interval notation for that, we have x such that x, let's see, how do I want to write this? X greater than or equal to negative 4 without x being equal to positive 5. And then in interval notation, that would be negative 4 to 5, and then 5 to infinity. All right, we're not going to include the value for 5, but we'll include everything larger than negative 4 or equal to negative 4. So there's the steps for finding the domain. Each one of these problems, you're going to consider initially that the domain is all real numbers, and then you can eliminate values as necessary. The example 7, express the area of a circle as a function of its radius. when we're expressing the area of a circle as a function of its radius, we all know that the area function of a circle is A is equal to pi r squared. Writing it in function notation, it would just simply be area as a function of r is equal to pi r squared. So we're not really changing anything, just notationally it's going to look a little bit different. Now, as far as the domain goes, think about a circle. Okay, we're talking about some generic circle here of radius r, and our independent variable here is the radius. What values do you think of when you consider the radius of a circle? What values do you consider to be impossible for that circle to have as a value of its radius? The first one that comes to mind is it can't have a radius of 0 because then it's not a circle. Similarly, we can't have any negative values because we can't have a negative radius. So this radius has to always be positive. So our domain will be all r's or radius values such that the radius is greater than 0. It cannot be 0 because, like I said before, if the radius is 0, then we have lost the circle as a defined circle, actually. So it can't be pi r squared. If we put in 0 for r, function goes to 0 and we don't have a circle. So we can add functions, we can subtract functions from one another, and you can see the notation here. For the sum, you just simply add function f plus function g, and the domains would include the intersection of function f and function g. So right here we have the domain of f plus g is the same as the domain of f intersected with the domain of g. With the difference, it's going to be function f minus function g, and that domain is the domain of function f intersected with the domain of function g. Same thing with multiplication. We can multiply functions together, and again the domain is the intersection of f and g. With the quotient function, where we divide two functions together, it's going to be for all x such that the denominator can't be 0, intersected with the other two domains. So we would have to look at 3 different components to that particular result to come up with the domain. And we're going to see that here in our next example. We have f and g being two functions defined as 1 over x plus 2, and then g of x is x over x minus 1. And we want to find these 4, I think that's it, yeah, just these 4 results. The first one is f plus g of x. So we will add those two functions together, and that's simply going to be 1 over x plus 2. That's f of x plus x over x minus 1. That's g of x. And when we simplify this, we need to look at when we're adding these two fractions together, or these two rational expressions. We multiply the left-hand side by x minus 1 over x minus 1. We're going to multiply the right-hand side by x plus 2 over x plus 2. This way we can get a common denominator between these two. So we end up with x minus 1, because that's x minus 1 times 1, plus, then we multiply x times x plus 2. We get x squared plus 2x over x minus 1, x plus 2. That's our common denominator. And we, excuse me, we can simplify this a little bit more. We end up with x squared plus 3x minus 1 in the numerator over x minus 1, x plus 2. I'm not going to expand that denominator, or not, I'd rather multiply it out, because I want to keep it the way it is. That helps with the domain restrictions. So for part A, we're looking for the domain. So let's first consider the domain of f. The domain of f is going to be all x values such that x can't be negative 2, because we see that makes that denominator undefined, or makes that function undefined. The denominator goes to 0. For function g, I don't know why I put a parenthesis there, the denominator can't be 0 again, so here we have x can't be 1. The numerator can be anything. And with our calculated domain here for the sum, remember that's the intersection of the domain of f intersected with the domain of g. So for this one, it's all x such that x cannot be -2 or +1. If you were to write that in interval notation, it would be from -infinity to -2. And then you have that union with -2 to 1. Then you have that union with 1 to infinity. And that's your interval notation for this problem. Alright, I apologize that I had to pause the video for a while. I had some interruptions that I had to deal with. It looks like I finished up part A. So for part B, we're doing the subtraction of the two functions. So it's going to be f minus g. And so we would set that up with function f minus function g. And again, we're just going to go through the process of simplifying. And we would do the same steps as we did previously, where we multiply both sides by the denominator of the opposite side. So instead of this line right here, what we would end up with is x minus 1 minus x squared plus 2x all over x minus 1, x plus 2. And then when we simplify that, we get x minus 1 minus x squared minus 2x. And we combine like terms in the numerator, and we finally end up with negative x squared minus x minus 1 all over our denominator. And with this one, with the difference, just like with the sum, our domain will still remain exactly the same, because if you look back at our notes, the domain of the sum is the intersection of the domains of the two individual components. Same thing happens with the difference. So our domain is going to be, I'm just going to write this for the sake of time, same as sum, and it's this right here. The next part that we want to look at is where we multiply these two together. So we're multiplying f times g. So we have 1 over x plus 2 times x over x minus 1. And when we multiply that, you multiply fractions. Remember, you multiply straight across, numerator times numerator, denominator times denominator. And we end up with x over x plus 2, x minus 1. And with this one, again, it's going to be the intersection of the domain, so it's going to be the exact same domain as we found in A and B. D, however, is going to be a little bit different. D is where we're doing the quotient of the two functions. So we have 1 over x plus 2 over x minus 1. Now when you divide fractions, you multiply by the reciprocal, so this is the same as 1 over x plus 2 times x minus 1 over x plus 2. And then when we look at the simplified form of this one, or sorry, I put x, that should just be x. We end up with x minus 1 in the numerator, because 1 times x minus 1, over x times x plus 2. So we still have the same initial two domain restrictions. We know that f, x can't be -2. That was what we found at the beginning. And for g, x cannot be +1. The only other thing we have to look at is our composed function, which we have right here. And for our composed function, we have to look back at that denominator again. And in this particular case, because of this x right here, we know that x can't be 0, because if we multiply this quantity x plus 2 by 0, then the denominator goes to 0, and we have an undefined function. So now we also have to include that x cannot be 0. So in our interval notation for the domain on this one, we have x cannot be -2, 0, or 1. In set notation. In interval notation, it's -infinity to -2, 2 to 0, -2 to 0, 0 to 1, and then 1 to infinity. So again, you can probably see why I prefer set notation to interval notation. But that is the end of part 2. I hope all that made sense. Again, remember to ask questions, and we will be meeting again on Thursday. So everybody have a great night, and I'll be talking to you soon.